Right now, I'm going to show you two videos which are connected by one interesting physical phenomenon. Did you already guess what the phenomenon is? Some of you who know a bit of physics said that it is the Doppler effect, and they are correct. The image illustrates the Doppler effect using an ambulance with a siren as the sound source moving from left to right. There are two observers. Observer on the right, as the ambulance approaches, this observer hears a higher frequency, higher pitch sound because the sound waves are compressed. Observer on the left, as the ambulance moves away, this observer hears a lower frequency, lower pitch sound because the sound waves are stretched out. The ambulance is depicted with sound waves showing the change in frequency as it moves, with the right side having closely spaced waves indicating higher frequency, and the left side having more spread out waves indicating lower frequency. Now imagine this ambulance going at a speed higher than the speed of sound. You would hear a sudden loud boom, known as a sonic boom, as the ambulance breaks the sound barrier. This creates shock waves that propagate outward in a cone-shaped wavefront, where the sound waves come very close together, resulting in a very intense pressure change. Okay, it's all cool, but why in the beginning would I show you the second video? By the way, it is a video of the nuclear reactor being switched on. The thing is that the light we see is an electromagnetic wave, so it behaves similarly to how sound waves behave under certain conditions. When an object, like a charged particle, moves faster than the speed of light in a particular medium, it creates a phenomenon known as Cherenkov radiation. This is analogous to the sonic boom produced when an object exceeds the speed of sound. But wait a second, doesn't Einstein's special relativity state that nothing can exceed the speed of light? This is only right in a vacuum. In water, light travels at a slower speed, and an electron, which is sufficiently accelerated, can exceed the speed of light in water. When this happens, an electron, which is a charged particle, produces electromagnetic radiation the same way an ambulance produces sound waves. If an electron travels at a speed that is higher than the speed of light, a light boom is produced. It looks like the blue glow you have seen previously. In everyday life, it is difficult to imagine the effects of special relativity happening, as you have to go at very large speeds to observe them. Cherenkov radiation is one of the effects that is caused by Einstein's relativity, and we can observe it in a beautiful blue glow when a nuclear plant switches on. Now let's talk about applications of Cherenkov radiation. There are several of them. Neutrino observatories. Large-scale neutrino detectors like the Super Kamiokande in Japan use Cherenkov radiation to detect neutrinos. When neutrinos interact with water or another medium, they produce charged particles that emit Cherenkov light. Cherenkov telescopes. Ground-based Cherenkov telescopes detect high-energy gamma rays from space by observing the Cherenkov radiation produced when these gamma rays interact with the Earth's atmosphere. Examples include the High-Energy Stereoscopic System, HESS, and the Very Energetic Radiation Imaging Telescope Array System, VERITAS. Cherenkov radiation elegantly illuminates the profound interplay between relativity and reality, providing a vivid window into how particles surpassing the speed of light in a medium reveal the deeper truths of our universe. This mesmerizing blue glow not only enriches our understanding of high-energy physics, but also underscores the remarkable ways in which the principles of relativity shape the fabric of our world.